I'd like to start by acknowledging the traditional owners of the location where I am presenting, the Wadi people of Dharawal country, and the traditional owners of the land on which I've undertaken much of this research. I'd like to thank the scientific committee of the first International Symposium on Coastal Ecosystems and Global Change. It really is an honour to be invited to present at this important meeting. For those who don't know me, my work largely focuses on low energy intertidal shorelines and how they change over time. Much of this work has been directed towards mangrove and salt marsh ecosystems, though I have also undertaken research on beaches, barriers, and estuaries. I'm variably described as an ecologist by geologists, or as a geologist by ecologists. I like to describe myself as either a geographer or an environmental scientist, as it allows me to straddle the sub-disciplines of the natural sciences, and I really enjoy the space that I'm able to work in. On the screen, I have a pretty striking image of a coastal wetland that has already been exposed to relative sea level rise. In this case, with the substrate undergoing subsidence in the order of about 1 metre. And the reason I include it here is because 1 metre of relative sea level rise is similar to what is projected to occur with sea level rise by the end of this century. And you can see that there is a very striking outcome with this degree of sea level rise. Sea level rise is a global change process that poses significant risk to coastal wetlands and the ecosystem services they provide. And it is in this space that most of my research occurs. In this talk, I would like to provide a brief synopsis of my research over the past 20 years, with the intention of sharing some lessons that I have learned. I hope that you are inspired to undertake research at your local study sites, as local research does have global significance. Here I have a video of tides inundating one of my study sites over a period of 3 days. And what you'll notice is that there is a rhythm to tides. They occur regularly. In this case, according to a semi-diurnal regime, and with a range of up to 2 metres. You see the channel filling and then reaching bank fill point and propagating across the wetland substrate. The rhythm gives an impression of stability, but this is far from what we actually see across longer timescales. Coastal wetlands are dynamic, and they are typically positioned at elevations near mean sea level and extend to the lateral limits of tidal inundation. Tides have a significant control on ordering of vegetation in coastal wetlands. And here we have a cross-section of mangrove forests in Darwin Harbour in Northern Australia. Here the vertical distribution of mangroves has been mapped from aerial photography, and zones have been differentiated on the basis of the influence of tides. In this case, we've got the Sonaradia zone extending down to mean neap tides, and the core mangrove zone dominated by Rhozophora, extending up to the height of mean spring tides. Beyond this, we've got the Cereops and salt marsh flats starting to dominate in those zones that are inundated much less frequently. The key point I'm trying to make here is that on a daily timescale, coastal wetlands are exposed to varying degrees of inundation, yet the vegetation adapts to this dynamic environment by ordering itself across the tidal gradient on the basis of the physiological tolerance of mangrove and salt marsh species to inundation and salinity. Tides bring varying amounts of sediment to substrates, and those areas that are inundated more frequently have a greater opportunity for sediment accumulation. If we extrapolate this process of sedimentation over longer periods of time, coastal wetlands increase elevation, and then they can begin to prograde and estuarine basins can infill. This variable pattern of infilling means that understanding the response of coastal wetlands to sea level rise is actually quite complex. And you might be wondering why I have a bathtub image on the screen. Well, it's to emphasize the point that wetlands actually behave nothing like a bathtub. Rather, as substrates change shape over time because of sedimentation, projecting the effect of sea level rise doesn't mean just filling out the bath. And this is where most of my work has been. It's trying to understand sedimentation patterns and how this will influence coastal wetland substrates, the distribution of vegetation, and the response of coastal wetlands to sea level rise across a range of timescales. And it's at this point I would like to focus on some geology. Geologists have been using the concept of accommodation space as a way of conceptualizing where coastal sedimentation occurs and how it changes over time. It's a particularly useful way as it provides a framework for understanding the processes influencing coastal sedimentation and shoreline change. The basic premise is that there is a three-dimensional space in which tidally borne sediments can accumulate. Accommodation space is bounded on three sides by the underlying lithology on which sediments can accumulate, shown here in grey. The landward limit of tidal inundation, which defines the extent of tidally borne sedimentation, in this case illustrated by the vertical limit of the highest astronomical tide. And it's also limited by the zone where hydrodynamic energy is too high to allow sediments to deposit and accumulate. Over time, we know that actually coastal wetlands occur roughly between mean sea level and highest astronomical tide. We get some idea of where that space actually occurs for coastal wetlands. Over time, accommodation space infills with sediment, which provides the soft substrate upon which vegetation can establish. And we tend to call this soft substrate realised accommodation. It's converted from available to realised accommodation space. We know, and as that realised accommodation space infills, the vegetation has to adapt and it shifts seaward so that it maintains its position between mean sea level and highest astronomical tide. We know that the sea is not level. Actually, it has rarely been stable, and over geological timescales, we also know that the sea is currently rising and its rise will accelerate throughout this century. This means that where the sea is rising, the height of tidal inundation increases, as shown here in red. And new available accommodation space is created both vertically and laterally. Together, the effects of sediment accumulation on realised accommodation space and sea level rise on available accommodation space means that accommodation space is actually always changing. And if we are going to improve models of the response of wetlands to sea level rise, we need to recognise the contribution of sediment accumulation and sea level rise on accommodation space. Here I have simplified processes influencing accommodation space down to sediment accumulation and sea level rise. But in reality, there is a whole suite of factors influencing realised accommodation space, including organic matter addition and substrate swelling. And there's a whole suite of factors that also influence available accommodation space, such as sediment consolidation, organic matter decomposition, and deep subsidence. So why am I talking so much about accommodation space? As tides come into wetlands, sediment delivery and accumulation will be higher where tidal inundation occurs more frequently. That is where there is more available accommodation space, in the mangrove zones down here. And it occurs less frequently where there's less accommodation space. If we can model the relationship between accommodation space and sedimentation, we have the basis for projecting the response of coastal wetlands to sea level rise. And this has been increasingly getting my attention. Fortunately, there's an archive of information about the response of coastal wetlands to past sea level rise that has accumulated within the substrates. And we just need to extract that archive to understand the responses of coastal wetlands to sea level rise across a range of timescales. This is where my work comes in. Back in 2000, along with Professor Neil Saintland, shown here in the bottom right-hand corner, we commenced an ambitious program of monitoring the elevation of coastal wetland surfaces throughout southeastern Australia and how they change over time. We used a technique known as the surface elevation table and marker horizon technique. And you can see me taking measurements from a surface elevation table in the middle picture. We call this an SET for short. I'm not sure what I would have said to Professor Sainsland back in 2000 if he had told me I would still be taking measurements 20 years later. But I'm hoping I can convince you, or at least myself, that this time commitment was worth it. This technique relies upon the establishment of a stable benchmark pole against which changes in substrate elevation can be measured over time. And this is done by measuring the height of these pins lowered to the wetland surface above the horizontal arm. This SET measurement is complemented by the establishment of marker horizons made from feldspar on wetland surfaces. And as tides come in and deposit sediment on top of the feldspar, they become increasingly buried. And we can come back later on and take a small core from the feldspar marker horizon location. We can measure the amount of sediment that's accumulated above the horizon. We typically find that the degree of vertical accretion measured from the marker horizons is different to the degree of surface elevation change measured from the SETs. And this is because of processes operating in the substrate within the realised accommodation space, which means actually that the substrate volume changes over time. And that change is not only related to surface sediment accretion, it's also related to things like decomposition of organic material and subsidence and compaction. We've established one of the largest regional networks of more than 120 SETs in wetlands extending from the subtropics into temperate Australia. At the time of establishment, these were the first SETs in the Southern Hemisphere. But now this approach is regarded as a global standard for monitoring wetland surface elevations over time. Since this time, we have been expanding our analytical approaches to consider changes in substrates in the context of accommodation space. And now we have access to a lot more positional data, such as that derived from global positioning systems and LiDAR data. We're also using tide gauge data a lot more widely, and we've got access to water level logger data so that we can determine tidal positions. We've also been undertaking a range of analytical analyses of the sediments and geochronological analyses to understand patterns of sedimentation change over time. The ultimate purpose in doing this is to generate data to establish the structure of models of coastal wetland response to sea level rise, and also to parameterize these models. Using our network of more than 120 SETs, we've been monitoring the surface elevation now for more than 20 years. Here I'm showing a typical SET plot. This one was generated a few years ago for the Tweed River, which is a subtropical estuary of Eastern Australia. We see some relatively consistent patterns throughout our region in our SET network. We also always see that the rate of surface elevation gain is higher in the mangrove zone, shown by these green points, where there is more accommodation space, and lower in the salt marsh zone, where there is less accommodation space, shown by the orange points. We can determine the rates of change in surface elevation within each of these zones. SET users typically make comparisons to rates of sea level rise from a nearby tide gauge, shown by the blue line. And where the rates of surface elevation gain is less than the rate of sea level rise, we call this an elevation deficit. There is some discussion amongst SET users about the appropriate timescale of sea level rise measurements for comparison of SET trends, as there may be a lag in the elevation response. So here I have shown that surface elevation trends in the mangrove, where there is high accommodation space, and in the salt marsh, where there is low accommodation space, is less than the rate of sea level rise over the study period and over a longer time frame as well. We've been playing around with new ways of visualizing our SET data, which allow us to better see the relationship between surface elevation change and accommodation space. Here I'm showing a graph from Homebush Bay, the site of the Sydney 2000 Olympics, but I've adjusted the elevation to be relative to the Australian height datum along here. And what this means is that the mangrove line shown in green, which at the start of our analysis period has significantly more accommodation space than the salt marsh, accumulated sediment and organic material at a higher rate. And over the 20-year study period, all of the elevations are starting to converge to the same height. Some modelers might call this an equilibrium elevation, and it's nice to see that actually our real empirical field data is starting to match what models are saying about equilibrium elevations. From the cores we've been extracting, we've been undertaking a whole suite of elemental and sediment analyses. But for this talk, I'm focusing on information about changes in accommodation space. And we've been undertaking a lot of geochronological analyses using ledger 10 dating techniques. Unlike typical approaches, what we've been trying to do is to position reconstructed wetland surfaces within the context of available accommodation space, here defined by the vertical range of mean sea level, indicated by the red points, and maximum sea level, indicated by the blue points. And this data has been taken from the nearest tide gauge with the long tide record. In this case, it's from the Fort Denison tide gauge, which has the second longest tidal record for Australia. What I'm showing on this graph is wetland reconstructions from about 12 cores from estuaries right near where I live, within 100 kilometres of where I live. And there are some patterns that we can see at this timescale, again, that relates to accommodation space. For example, salt marsh substrates, which have relatively little available accommodation space, increase at rates equivalent to the rate of increase in maximum sea level. Mangrove substrates are increasing at rates slightly higher than observed rates of sea level rise at this timescale, whilst mudflats positioned lower in the tidal frame are again increasing at rates equivalent to sea level rise. So we're seeing that most of the surfaces are increasing at rates equivalent to sea level rise, but mangrove surfaces are increasing at rates exceeding sea level rise, indicating that progradation is occurring. Whilst I've been trying to resolve the discrepancy around sedimentation across different timescales, I've also been thinking about the variation spatially. We do see variation across the intertidal zone on the basis of accommodation space, but I also wanted to look at variation at larger spatial scales as well. Here I have extracted a table from Ken Krause's paper on how mangrove forests adjust to rising sea level. When you start to look at the rates of surface elevation change in our mangrove forests of about 1 to 3 millimetres a year and compare this to the global literature, we can see that actually our rates of surface elevation change are considerably lower. And this was a little bit concerning. In addition, I was also comparing the composition of accumulating sediments and noting that our substrates were much more mineral dominated than elsewhere. And here I have extracted a graph from Karen McKee's work in Caribbean mangroves, where she has found that organic material, fine roots and coarse roots, was a significant and a dominant component of elevation adjustment. By contrast, a national scale analysis found that soil carbon stocks in Australian vegetated coastal ecosystems was a little bit lower than global estimates, over 1 metre depths, and also there were lower rates of sequestration. In combination, our low rates of sedimentation and low rates of organic matter suggest that the capacity of Southeast Australian coastal wetlands to adjust to sea level rise is less than what I was seeing in the global literature. And that was a little bit concerning. The question I was trying to resolve was why were we finding different patterns in Australia compared to researchers elsewhere, particularly as we were not seeing the same degree of loss of wetlands as I was seeing in North America in particular. And when you delve a little bit further into the work of Karen McKee, she was able to demonstrate that the pattern of organic matter accumulation over time coincided with a long period of sea level rise over the past 10,000 years. This pattern of sea level rise is substantially different to the pattern of sea level stability in Australia over the past 7,000 years. It was at this point I was starting to think that sea level change over millennia may contribute to the variation I was seeing. So I looked a little bit further. I wanted to look at what the prevailing view on global controls of organic matter addition and carbon storage within coastal wetlands was. Early global scale carbon studies for coastal wetlands primarily related carbon stores to climatic factors. This includes the first mangrove carbon budget by Twilly and the Global Review of Sedimentary Organic Matter and Carbon by Chumra, which point to global variation being related to factors that vary across latitudes, things such as temperature and rainfall. The premise being that these factors influence rates of decomposition of organic matter. Some of the more recent studies have applied sophisticated modelling approaches and started to transition towards ecosystem-specific factors as controls on soil organic matter and carbon storage. For example, Sanders et al. Considered the influence of temperature, tidal range, latitude, and rainfall on mangrove carbon stores, finding that rainfall described 86% of global variability. Not surprising given that mangroves are largely tropical plants. Revi related carbon storage in mangrove soils with coastal environmental settings, which primarily refers to estuary geomorphology. And Sandeman linked mangrove carbon storage to imagery, tidal range, and suspended sediments. There's a couple of patterns emerging in these analyses. First, there is increasing focus on understanding mangrove carbon dynamics, and I suspect this is because there are reasonably good global data sets of mangrove extent. And I note that there's been some very high resolution mangrove maps being generated in China by Zhang et al. The same doesn't exist for salt marsh or seagrass due to difficulties in distinguishing their extent using remote sensing. And I really encourage remote sensors to continue in their efforts to map the global distribution of salt marsh and seagrass. Second, there has been increasing recognition that coastal ecosystems are not fully terrestrial and that factors influencing oceans will have an important control on carbon stores. Finally, more data is being generated from the Southern Hemisphere, and this has meant that prevailing views regarding global controls on coastal wetland carbon storage being related to climatic variables are beginning to fail. In particular, there was notably less carbon storage within coastal wetlands of Australia compared to wetlands at similar latitudes or climates in the Northern Hemisphere. And Sandeman in particular emphasised the inability to develop a global model of carbon storage to depth of 1 metre. And I'm hoping that you can see the plot twist that is coming. So let's think about global scale accommodation space and how it has changed with sea level rise over long periods of time. In Australia, we are located literally half a world away from regions of highest ice sheet extent during the last glacial maximum. Since this time, global eustatic sea level rose approximately 125 metres and has been relatively stable for the past few millennia. Here is a relatively old map of Holocene relative sea level zones and relative sea level curves for each of these zones. As Australia is located so far from land-based ice sheets, our pattern of sea level changes has not been influenced by lithospheric adjustment as ice sheets melted. This means that for Australia and many regions in the Southern Hemisphere and throughout Asia, relative sea level changes on our shorelines were similar to global eustatic patterns of sea level change. It also means that the height of the upper boundary of available accommodation space has been relatively stable for the past few millennia. Elsewhere around the world, the position of the land relative to the sea has not corresponded to eustatic sea level patterns because the Earth's lithosphere has tilted and rebounded as ice loads diminished. For much of the Northern Hemisphere, sea level has a longer history of rising than it has in the Southern Hemisphere. This means that Australia is an ideal place to consider how accommodation space changes without sea level rise occurring. And these are the conditions under which I was collecting my data. Based on the differences that we were seeing in sedimentation in Southeast Australia, we hypothesised that perhaps variation in relative sea level rise across the globe could explain large-scale variation in both sedimentation and organic matter accumulation. In particular, we propose that under stable sea levels where accommodation space increasingly diminishes, that wetland substrates become increasingly dominated by mineral sediment addition and organic matter decomposition. and that where sea level had a longer history of rising, new accommodation space was always being created, and organic material that accumulated within the accommodation space was less likely to decompose because it became increasingly submerged by rising sea levels. We initially did a large-scale literature search and collected all the data we could find on core-based carbon storage within salt marsh. We focused on salt marsh because they were more globally distributed across the relative sea level rise zones than mangroves. And on the map in the top of this slide, you can see the red points where all of our data came from. This search was supplemented by additional core data extracted from the new Coastal Carbon Research Network database developed in the USA by Patrick McGonigal. And access to this data included a lot of information coming from China. We also reached out to Janine Adams in South Africa and collected a lot of additional core data from South Africa and had a lot of our own data to add from Australia. So the outcomes of this study has now been published in Nature in 2019. And what we found is that when you compare carbon storage across the zones, it was typically higher where sea level continued to rise. Zones 1 and 2. This is because it created more accommodation space. We also found that there was more down core preservation of carbon when sea level was rising, demonstrated down to depths of 3 meters. And this is because the rising sea levels preserved the carbon. Now, this was different to what we were seeing in our core data for the zones that were further away from the maximum ice sheet extent and where sea level was not rising over the past few millennia. At this point, I would like to circle back on whether the prevailing views on global carbon storage remain true. You will remember that early models largely related carbon storage to temperature and latitude, and some of the later models brought in ecosystem-specific factors such as tide range and sediment supply. Now, these are important, but I would argue that it's not surprising that global models linked carbon to temperature and latitude because they largely excluded data from the Southern Hemisphere and from Asia. And once you include this, it throws those patterns into disarray. These are the regions where carbon storage has been influenced by long periods of sea level stability. Subsequent models built upon the foundation of temperature being a predominant control, therefore struggled to adequately ascribe controls on carbon storage at global scales. Our analysis found actually at a global scale, carbon storage is neither related to climate or variation in salinity. We've extended this analysis further by considering what geological evidence we have to indicate the threshold of mangrove survival under rapid sea level rise. And this work was published last year in Science. Again, we went through the records to find evidence of mangrove sedimentation rates over the Holocene, derived from radiocarbon dating of mangrove organic material, to understand what rates of sea level rise were too high for mangrove to increase elevation vertically through the accumulation of mineral and organic material. Broadly, we found that rates of vertical elevation gain were higher during the early Holocene. This is shown in the first map. And it's higher during the early Holocene than it was during the mid to late Holocene, shown in the second map. So we've got variation in sedimentation across time. However, there was some variation in this pattern globally that again related to variation in relative sea level rise and how this influenced available accommodation space. More specifically, what we found is that locations far from regions of maximum ice sheet extent, here labelled far field locations and representing much of the mangrove of the Southern Hemisphere. In situ vertical accretion commenced approximately 8,500 years ago, and the rate of vertical accretion, shown by the green line, corresponded to exceeded sea level rise, shown by the red line. In contrast, intermediate field locations that were closer to regions of maximum ice sheet extent and have a much longer history of relative sea level rise over the past few millennia had initiation of vertical mangrove accretion only at 7.7 thousand years ago. This is when sea level rise started to slow down a little bit. And after this time, they only tracked what sea level was doing, as shown by the purple line sitting on top of the green line. From all of this information, we wanted to work out whether there was a threshold of sea level rise that was too high for mangrove to maintain their lateral position through vertical growth of the substrate. Using a Bayesian modelling approach, we found that intermediate field locations exhibited only a 10% probability of initiating vertical growth when sea level rise was 5.7 millimetres per year. This was less than the 7.1 millimetres a year identified for far field locations under the same probability. And it may relate a little bit to sediment supply and a few other factors. Overall, when you pull all of the data together, what this indicates is that there is a 10% probability at a global scale of mangrove initiating vertical growth at rates matching or exceeding relative sea level rise of 6.1 millimetres a year. So what we're starting to do here is identify the threshold of sea level rise that becomes too high for mangroves to maintain their position through vertical growth. So we're starting to get to those thresholds. We're pretty excited by this. So I'm now hoping you're convinced of the influence of relative sea level changes both in the past and in the future on coastal wetlands. I'd like to spend some time making some generalisations about how coastal wetlands in the Northern Hemisphere and the Southern Hemisphere have responded to sea level rise in the past and what this means for future adaptation. On the screen, I have two images. On the left is a scene of the Mississippi Delta, which is increasingly losing elevation with respect to the tidal frame due to both subsidence and sea level rise. On the right, I have a scene of the broad coastal floodplains of the Gulf of Carpentaria in Australia. Here it is flooded during the wet season. I've chosen this image intentionally because it shows how broad the floodplains are, how much progradation of the floodplain has occurred over the past few thousand years because of stable sea level conditions. So broadly speaking, what we see in the Northern Hemisphere is that soil organic matter tends to be higher and extend to greater depths. And rates of surface sediment accumulation is markedly higher as accommodation space has continually been created over the past few millennia. By contrast, in the Southern Hemisphere, where accommodation space has increasingly become limited over the past few millennia, soil organic matter decomposition predominates, particularly in portions of the floodplain where tidal inundation has become limited. So in the saline upper intertidal flats and in salt marshes. Stable sea levels have facilitated the infilling of accommodation space, and creation of new accommodation spaces only occurs through progradation, resulting in the development of broad low-lying estuarine and coastal floodplains. Importantly, the influence of sea levels over the past few millennia has been inherited into the coastal landscapes of today. Accordingly, as wetlands have already been responding to sea level rise in the Northern Hemisphere, their resilience will become increasingly tested if sea level continues to rise as projected. And there is already evidence of this effect, with significant shoreline erosion and marsh breakup in these regions. Most projections coming from North America in particular indicate reworking of soil organic matter and increases in carbon dioxide emissions due to sea level rise. And we're already seeing this occurring in the Mississippi Delta. In the Southern Hemisphere, the broad coastal and estuarine floodplains will become hotspots for contemporary blue carbon generation as vegetation communities retreat to high elevations. And there is these broad coastal floodplains that provide the space for that to occur. This retreat, however, will be dependent upon how we manage coastal landscapes, and there is the risk of having coastal squeeze effects emerging. To finish, I'd like to bring the talk back to me and what I have learned. I've got a picture of me doing fieldwork because it's really because I want to emphasize the lessons that I've learned regarding the value of the data that I was collecting from my local wetlands. It was from these data that we began to question prevailing views on controls of carbon within coastal wetlands at a global scale. And we were beginning to question their long-term resilience to sea level rise. Our local data not only conflicted with prevailing views, but it forced us to reconcile the information we were finding. And the outcome has been a greater appreciation of the role of sea level rise in shaping coastal wetlands now and in the future. And we're now seeing this as being a predominant parameter included into models. So in finishing, I encourage you all when you're doing your work to think global, but do this by acting local. And this is achieved by continuing to collect local data so that we can improve model development, not only at the local scale, but also at the global scale. Finally, I would really like to acknowledge all the people who've supported financially the research I've undertaken, including the Australian Research Council, my own university, and the New South Wales and Victorian governments. Many colleagues, students and volunteers have contributed to this research and all deserve special acknowledgement. Key research partners and past research funders include ANSTO and the New South Wales Government and the USGS, and I really want to thank them. And finally, I really do want to thank the organising committee of this conference for this invitation. It's been a great meeting and I hope you found my presentation helpful. Thank you.